All right, let's dive into some physics today,
Sounds good.
specifically projectile motion,
Okay.
but with a bit of a twist. Springs.
All right.
You said us pretty cool stuff on this topic,
Yeah.
including this interactive simulation from Singapore.
Yeah, the projectile motion with system of masses and spring simulation.
Right.
It's a great example of an open educational resource, letting people actually explore how forces interact.
Yeah, exactly. So it's not just equations on a page.
Right.
You can really see how things like mass or spring stiffness or even gravity
Right.
affect how objects move.
Absolutely.
To start, can you walk us through the basic setup?
Okay.
What are we actually looking at in this simulation?
So imagine two masses, like balls,
Okay.
connected by a spring.
Right.
The whole system can move around,
Okay.
but only in 2 dimensions.
Got it.
And there's this really neat feature
Yeah.
where you can turn gravity on or off,
Oh, wow.
which really changes things.
So I can make these balls bounce around, connected by a spring,
Yep.
and I can decide if gravity is involved or not.
Exactly.
It's like a physics sandbox.
Yeah, it is.
What are some of the key principles that this simulation is trying to demonstrate?
Well, one of the big ones is Hooke's law,
Okay.
which states that the force you need to stretch or compress a spring
Yeah.
is directly proportional to how much you change its length.
Okay.
Think about like heavy-duty springs,
Yeah.
like they use in car suspension.
Uh-huh.
So the car's weight compresses the springs,
Okay.
and they push back with a force determined by how much they're compressed.
That makes sense for a car that's sitting still.
Right.
But this simulation is all about movement.
Uh-huh.
So how does Hooke's law come into play
Good question.
when these masses are actually in motion?
That's where it gets really interesting.
Right.
As these masses move,
Yeah.
the spring is constantly stretching and compressing,
Right.
so it's always exerting forces on them. And the simulation calculates these forces at every single instant
Wow.
based on Hooke's law.
Interesting.
And that determines how the masses move.
So the more the spring stretches,
Yep.
the stronger it pulls the masses back together.
Exactly.
And the more it's compressed, the harder it pushes them apart.
Right.
Okay.
So it's this constant push and pull,
Yeah.
along with the initial conditions you set,
Wow.
like how fast the masses are moving at the start.
Okay.
That determines the whole dance they do.
And I imagine gravity adds another layer of complexity
Oh,
to
absolutely.
the movement.
With gravity turned on, you'll see these parabolic arcs, like when you throw a ball.
Right, right.
So the simulation has to factor in both the spring force and the downward pull of gravity
Okay.
to get the motion right.
That's really impressive.
It is.
The source material also mentions something called a damping term. What does that mean in this simulation?
Damping is basically energy dissipation. It means that in the real world, systems lose energy over time
Right.
due to things like friction or air resistance.
Okay.
Like imagine a pendulum swinging back and forth.
Yeah.
Eventually it'll come to a stop.
Right.
It's damping.
So without damping, the masses in the simulation
Yes,
would just keep bouncing and oscillating forever.
exactly.
Wow.
The damping term makes the simulation more realistic.
Oh.
You can even adjust how strong the damping is, which controls how quickly the system loses energy.
It's amazing how much detail they've packed into this.
I know, right?
I'm starting to see why you were so excited about it.
It's a great tool for visualizing these concepts, and we're just getting started.
Right.
The source material actually suggests some activities
Right.
we can try with the simulation to really see these principles in action.
Let's dive into those.
All right.
I'm ready to start playing in this physics sandbox.
Sounds good.
All right, so we've got the basics down. Two masses, a spring, moving in 2 dimensions, with or without gravity.
Right.
We talked about Hooke's law and damping,
Yeah.
but I'm ready to actually try some things out.
Me too.
What kind of activities does the source material suggest?
Well, there are a few
Okay.
that really highlight how even small changes can lead to big differences in the results.
Okay.
One suggestion is to give one of the masses an initial velocity.
So like giving it a push?
Yeah, like a flit.
Okay, so we're setting things in motion right away.
Exactly.
I'm guessing the path of the masses will look different depending on whether gravity is on or off.
You got it.
With gravity, we should see that familiar arc.
Right. Like a basketball being thrown.
But without gravity,
Yeah.
It's all about the spring force and that initial momentum.
Exactly.
It'll be interesting to see how those interact.
It is.
And what about changing the mass of one of the balls?
Oh, that's a good one.
I bet that throws a wrench in things.
It does.
Remind me about the car suspension analogy again.
Sure.
Okay.
So if you add a bunch of weight to a car,
Yeah.
the springs compress more.
Right.
And the car sits lower.
Okay.
It's the same here.
So by changing the mass of one ball, we're changing the center of gravity of the whole system.
Exactly.
So if one ball is a lot heavier,
Yeah.
it's going to have more influence over how everything moves.
Right.
The heavier mass pulls harder on the spring.
Exactly.
And that affects both masses.
Yep.
This is making me think about all sorts of real-world systems that use these principles.
Oh, absolutely.
Like we talked about car suspension.
Yeah.
But what about like a bow and arrow?
Oh, yeah. Great example.
You pull back the string, storing energy in the bent wood, and then releasing it to shoot the arrow.
Classic projectile motion.
With a spring-like force involved.
Right.
I never thought of it like that.
It's amazing how these simple physics concepts are all around us.
Speaking of which, I thought it was interesting how the source material talked about open educational resources.
Oh, yeah.
Like this simulation.
They're so important.
It's great that anyone can access this, no matter their background or resources.
It makes knowledge accessible to everyone.
Exactly.
It's really about breaking down those barriers to education.
And fostering a community of learners.
Absolutely.
So we've talked about initial velocity, changing mass, and the value of these open educational resources.
Right.
What other activities does the source material suggest?
Well, there's one you mentioned before that I think is particularly fascinating.
Okay.
We've been exploring the system in 2 dimensions.
Yeah.
But the source material asks, what if we added a third?
Oh, yeah, that's a great question.
Going from a flat surface to a whole new spatial realm.
How would the masses and the spring behave differently?
Well, that would require a more complex simulation to fully explore.
But we can still speculate.
Of course.
Would the masses move in spirals? Or would we see completely new kinds of oscillations?
Yes, possible.
I'd love to see a 3D version of this.
Me too. It'd be amazing.
Imagine being able to rotate the viewpoint.
Yeah.
And see everything from all angles.
A whole new level of understanding.
It makes you realize how much we're simplifying things by working in just 2 dimensions.
But that's part of the process, right?
Yeah.
Start with the basics, build from there.
And even in 2 dimensions, there's still a lot we can explore.
You got it.
We can adjust the spring constant and the damping coefficient.
In real time.
It's like we've only just scratched the surface.
It's true.
So much to discover.
It's a deep dive for sure.
Well said.
Thanks.
Before we get too lost in all this physics, let's take a minute to recap.
Okay.
We've explored the basic setup of this simulation. We talked about Hooke's law, damping, even imagined a 3D version. And we talked about real-world examples.
And open educational resources.
It's been quite a journey.
It has.
And we're not done yet.
Oh.
There's still more to uncover in the simulation.
Right.
We can change the mass, adjust the spring constant and damping coefficient. And don't forget all those other resources mentioned in the source material.
So much to explore.
We'll dive into all that in the final part of this deep dive.
Sounds good.
Welcome back. We've been having a blast with this spring-loaded simulation.
It's pretty cool, right?
We've covered a lot of ground Hooke's law, damping, even a hypothetical 3D version.
Right.
But now I'm itching to get hands-on.
Me too.
Really play around with the variables.
Well, the source material has us covered there.
Okay.
Remember those activities we talked about?
Yeah.
Changing the mass, tweaking the spring constant, and damping?
Yeah. Let's start with the mass. You mentioned it's like changing the weight on a seesaw. So if one mass suddenly gets a lot heavier, how does that affect the whole system?
It's like having 2 kids on a seesaw.
Right.
If one kid is way heavier, the seesaw tilts like crazy.
Right, of course.
Same thing here.
So by increasing one mass, we're shifting the center of gravity.
For the whole system, exactly.
Meaning the heavier mass pulls harder on the spring, affecting both masses.
It's all connected.
And the simulation lets us see this happen.
Oh, absolutely.
How the spring stretches differently, how the masses move.
It's a visual way to understand a key physics concept.
Really cool.
It is.
Okay, what about the spring constant?
Right.
What happens when we make the spring stiffer or looser?
Think of it like a rubber band.
Okay.
A stiff spring is like a really tight rubber band.
Got it.
Takes more force to stretch it even a little.
So in the simulation, Increasing the spring constant means?
It means the spring will resist stretching and compressing more strongly.
Meaning the masses wouldn't move as far apart or as close together.
Exactly.
Would that change how fast they oscillate too?
Good question. Yes, it would.
Okay.
A stiffer spring would lead to faster oscillations.
So they'd be moving back and forth quicker.
Exactly. Think of a tight guitar string.
Right.
Vibrates faster than a loose one.
That makes sense.
Yeah.
And what about the damping coefficient? We talked about it before.
Yeah.
But I'm still not totally clear on how it works.
Okay, well, remember, damping is all about energy loss.
Right, like a bouncing ball.
Perfect example.
Each bounce loses a little energy until it eventually stops.
Right, so the damping coefficient in the simulation controls how quickly that bouncing dies down.
A high damping coefficient means the system loses energy fast.
Exactly, like bouncing a ball on a thick carpet.
Okay.
Low damping is more like bouncing on a hard floor.
It's like having our own physics lab.
It is, isn't it?
We can tweak these variables and see what happens in a controlled way.
It makes it all so much easier to grasp.
And it's amazing to think how these principles apply in the real world.
Oh, definitely.
We talked car suspension.
Yeah.
But the source material also mentions things like launching rockets.
Right, or even just a bouncing ball.
It's mind-blowing that the same laws govern planets and springs.
I know, right?
Physics is really about how the whole universe works.
At its most fundamental level.
Makes you appreciate how everything's connected.
It does.
Before we go too deep down that rabbit hole, though, I wanted to mention those other resources.
Yes, the additional materials.
Other simulations and things.
There's so much out there.
For anyone who wants to learn more.
A ton of information.
The source links to all sorts of stuff.
Nice.
Simulations of projectile motion with air resistance.
Right.
Even classic models from, like, Walter Fendt.
He's a legend.
It's great to know there's so much more to explore.
It really is.
Even after this deep dive.
Learning never stops.
Well said. Well, that brings us to the end of our deep dive. Into the world of projectile motion with a springy twist.
It's been a fun one.
It has. Thanks for joining us on this exploration.
Of course.
We hope it's made you curious.
Yeah.
Maybe even inspired you to try some of these simulations yourself. And remember, the learning doesn't stop here.
Nope.
Keep those minds curious. Keep exploring.
Absolutely.
You never know what amazing discoveries you might make.
You never do.